The next law that I want to discuss is the inverse law. So an informal definition, a way to get us started talking about the inverse law, is using our operation. It's a way to get back to the identity. So let's read the formal definition. Two elements are said to be inverses of each other, and they form an inverse pair, we call it, if the result is the identity when we use this binary operation. So apply two things, put them together. If you happen to get the identity out of the deal, you found an inverse pair. So if we look closely at the equation below, it's saying if AB, when we put AB together, or you could do it the other way around, if you put B and A together, if our operation is star, if you happen to get the identity back out of that, then A and B are said to be inverse pairs. Let's try an example with our meets table. So in the meets table below, what we can do if we're trying to search for inverse pairs, if we want to find all of the inverse pairs, we can scan our table to find the identity. Now if we remember back to a previous video, the identity is surprised. So our identity appears there in the table, it appears there, and it appears there. So if we are searching for inverse pairs, we need to search for all of these combinations. So if we want to write down the inverse pairs, let's make a labeling, H for happy, U for unhappy, and S for surprised. You could say that unhappy and happy, when they meet right there, you get surprised out of the deal. Now, we should also make sure that this works out in the opposite order, and it does. If happy first meets unhappy, we also get surprised. So we can safely say unhappy and happy are inverse pairs. There's one more inverse pair in our table. When surprised meets surprised, you also get surprised. So S meets S gives us S. The two inverse pairs that we can find are unhappy with happy and surprised with surprised. We can notice that the identity always pairs with itself because the identity can just disappear with the operation and you have found a way back to the identity. Okay, so the whole idea of talking about inverses is really valuable. It allows us to set up equations and solve the equations, which has many applications in real life when we're maybe doing some kind of modeling and we need to solve for a particular variable in our equation. So we've set up that type of thing below, where we have happy meeting the result of our unknown x with unhappy. X is one of happy, unhappy, or surprised. We don't know which one. We have to find out which one will give us happy as the result. And we can't do this by guessing and testing, or we're not going to allow ourselves to do this by guessing and testing. We want to use the inverse property to help us out here. So anytime you've been taught to solve equations, even if you had never heard of the word inverses, you must have been using inverses because it's the way that we undo our operation. So the first thing that we would like to do is undo happy meets. So the way that we can do that is apply unhappy to both sides of the equation. If we apply an unhappy on the left and an unhappy on the left, the result of unhappy and happy is surprised. So that becomes surprised, and in the brackets we still have the same thing, x, unhappy, nothing changed there, and on the right-hand side we happen to have unhappy and happy, that makes surprised as well. So the nice thing about applying that inverse to both sides is you got the identity out of that, which is surprised, and the identity can now disappear. So we are left with just x, unhappy, on the left-hand side, which is the same as surprised. So the next thing that we'd want to do is apply the inverse to unhappy on the right-hand side. So if we do that, the inverse of unhappy is happy. So if we apply that to both sides, our equation is still equal because we've done the same thing to both sides of the equation. And finally, what we can get is x isolated all by itself when the surprise disappears. So we get x is the same as happy. Okay, now I'd like to discuss the uniqueness of inverse pairs. So each element in our set can only be paired with one other element, or possibly itself, to form an inverse pair. Now we do need one tool to help us out with that, and that is we need to have our operation being associative. So to do this proof, what we're going to do is say we have A, B as inverse pairs, and A has another pair with C. So C and A are inverse pairs, and A and B are inverse pairs. So we're going to try to evaluate this expression, CAB, cab. We're going to evaluate cab in two different ways. We're going to suppose that C and A are inverse pairs, and A and B are inverse pairs. So what happens if A and B are inverse pairs? They become the identity, and the identity disappears, and you just get C. On the left-hand side, again, the identity comes out of the inverse pair. When we combine that with B, the identity disappears, and we just have B. And if we notice, B is the same as C through this chain of equality. So we tried to pick two different inverse pairs for A, B, and C, but we discovered that B is equal to C. So this is what we mean by there is only one way to make the pair. If you try to make it in two different ways, you will end up with two elements of your set that are actually the same. Okay, let's discuss additive inverses and multiplicative inverses. So the sign that we use to, say, take the additive inverse is a dash, or -2. It means take the additive inverse of 2. So what is the additive inverse of -2? We would be searching for the way to get back to the identity through addition. So how do we find out what to put right here in our equation so that the equation works out? And of course, the number that we're looking for here is 2. So -2 plus 2 gives us 0. 2 is the additive inverse of -2. In part B, we want to discuss the additive inverse of 0. 0 is the identity, so it always pairs with itself. The way to add something to 0 to get back to 0 is simply 0. So 0 is the additive inverse of 0. Okay, so some similar discussion now for multiplication. The symbol that we used for additive inverse was a dash. The symbol that we use for take the multiplicative inverse is raised to the power -1, raised to the power -1. And in real numbers, this is equivalent to taking the reciprocal. So what is the multiplicative inverse of 2? The multiplicative inverse of 2, what we would be looking for is 2 raised to the power -1. What is this? We want to find out what do we multiply 2 by to get back to the identity, which is 1. What do we put right here? How do we figure out what that number is? We just have to solve for that question mark. And after a few moments of thought, we'll realize that this number that we need to place right there is 1/2. So 1/2 is the multiplicative inverse of 2. In part B, we are asking what members of the set of rational numbers, so the fractions, have multiplicative inverses. So if we think about all of the numbers that we're allowed to take reciprocals of, we can do this most all of the time. It's just when we have 0, if 0 is our numerator, and it doesn't really matter what our denominator is, this number is just 0 to begin with, we can't take the reciprocal of this. We can't flip that around, because if we do that, we end up dividing by 0. So what members of the set of rational numbers have multiplicative inverses? Everything but 0. So all rational numbers other than 0. Okay, so to wrap up this discussion, let's try to solve an equation with real numbers for x. Let's say that we have 2x minus 2 is equal to, let's say, 4. If we are searching for this x, what we'd want to do is apply the inverse to both sides of the equation. So let's apply the inverse of minus 2 first. That's plus 2. So we would add plus 2 to both sides of the equation. We wouldn't change the result of our equation by doing that. Our equation is still true. Now we are searching for the 2x that equals 6. So finally, to finish this off, the inverse of multiplying by 2 is to multiply 1/2 on both sides of the equation. So if we do that, we finally find out our result. Our result is that x equals 3. So the point of this discussion is to notice that inverses help us solve equations.